Our paper is titled Uncertainty Quantification of Surrogate Explanations, an Ordinal Consensus Approach, and I'm Jonas Schulz. So what is the problem we address in our paper? So given an image and an image classifier, we would want to obtain an explanation for why the classifier classified this image here depicted on the left-hand side as a bird image. And for this, we would first segment the image into interpretable components of which we think might lead to an insightful explanation. And then we could derive a so-called surrogate explanation. And the surrogate explanation assigns to each of these interpretable components we segmented the image in the form of superpixels a value. And this value could be interpreted as a feature attribution. And so this surrogate explanation could be represented in the form of this heat map, where we could infer that the bottom left superpixel is of most importance to the classifier because it has been given the highest feature attribution value to. However, though, we as users or practitioners of this technique are not really informed about a measure of trustworthiness or how much uncertainty this explanation is entailed with. And in our paper, we propose to measure this trustworthiness by the amount of consensus among a diverse set of surrogate explainers. But yeah, what are surrogate explanations in the first place? So surrogate explanations have been first proposed in the LIME paper, whereas LIME stands for Local Interpretable Model Agnostic Explanations. And I'll just quickly go through the procedure here depicted on this 2D schematic. So we have a black box classifier represented through this black line, which classifies data points with the two features S1 and S2 into different classes. And for a query point, here the black dot, we would want to explain the decision of the black box classifier. And in the first instance, we would create perturbations of this query point, here represented by this yellow area around the query point. And these perturbations are meant to be similar to the query point. And these perturbations could be then fed into the black box, of which we would obtain class probabilities. And then based on the set of perturbations of the query point and the class probabilities from the black box, we could fit a linear interpretable model to this new data set, which we refer to as the surrogate or the surrogate explainer. And by inspecting the weights or coefficient of the surrogate, we could then infer about the importance of the input features. Of course, this method is not without issues, and it assumes that the surrogate is approximating the black box it is trying to explain well enough locally. However, though, if we were to run the LIME procedure multiple times, we would end up with different surrogate explainers. And one reason for this is the perturbations we would randomly generate at runtime. So if we were to run LIME multiple times, we would end up with different surrogate explainers because each time we would generate new perturbations, which are then fed into the black box classifier, and we would obtain different predictions and thus a different set to which we fit the surrogate explainer to, which is here depicted on the right-hand side as compared to the standard LIME procedure on the left-hand side. So if we were to run the LIME procedure 100 times, for instance, on this image, which we segmented into 8 superpixels, S1 to S8, we would not end up with a fixed set of surrogate coefficients, but actually with distributions, which are here depicted as a violin plot on the right-hand side. And whereas it might be still quite easy to see that perhaps surrogate coefficients S7 is of highest importance to the classifier because it has been given the highest surrogate coefficient here in black. The order of importance between the superpixels S7 in red and S4 in cyan is not that clear because the distributions of these surrogate coefficients overlap. In our paper, we also argue that the predictive uncertainty of the model can be seen as another source that induces instability into the surrogate derivation method. So if we were to run Lime on a fixed set of perturbations, but we now considered our black box to actually be an ensemble of multiple black boxes, we could still induce diversity among the surrogate explainers by sampling the predictions for the perturbations randomly from the ensemble member, which is here depicted on the right-hand side. So again, coming back to our introductory example, we had the bird segmented into 8 superpixels. By running Lime 100 times, but on a fixed set of perturbations, now we were sampling the predictions randomly from the ensemble members, we would again end up with a distribution of surrogate coefficients, which is not that easy to reason about since the distributions of these surrogate coefficients overlap partially. Having mentioned these two sources to induce diversity among surrogate explainers and to generate a set of surrogate explanations, we could aggregate multiple diverse explanations. And this has been proposed in the references as number 2. And here the authors propose to aggregate the information contained inside these multiple surrogates through a rating scheme. So we can see these surrogates as raters that assign a rank to each of these superpixels. And the rank could be assigned as such. The superpixel assigned to the, or given the highest feature attribution to, would be given the rank 8. Second highest feature attribution would be rank 7, and so on. And we could do this for multiple surrogate explainers and store this information into this rating table here depicted on the bottom. In our paper now, we propose to measure the amount of trustworthiness that is associated with this aggregated explanation by the level of agreement or the level of consensus among these diverse surrogate explainers. And we could do this in 2 ways. So one way would be to address the consensus for individual superpixels. And here we can see, based on this rating table, that the rating with regards to superpixel S7 has a high agreement, because most of the superpixels gave this, most of the surrogates gave this superpixel a high value. The agreement is rather low for the superpixels S1 and S2 because the surrogates gave these 2 superpixels a very different rating. So this could be one way to address the consensus. And another way would be to consider the overall agreement with regards to all superpixels at once. And for this, we used 3 different measures that consider the consensus for all superpixels at once. Would be Kendall's coefficient of concordance, or short W, and Fleiss kappa, short kappa. Whereas Kendall's coefficient of concordance is, or has been originally designed for these ordinal scale ratings, Fleiss kappa could be also used for categorical ratings or nominal scales. And these 2 measures are scaled from 0 to 1, where 0 means no consensus among the surrogates, and 1 means full consensus or full agreement. And by using these 2 different measures, we draw a different picture of the explanation's uncertainty. The measure to address the consensus for individual superpixels would be the ordinal consensus C, which is also scaled from 0 to 1, whereas 0 means highly polarized rating. 0.5 means no consensus among the surrogates, and 1 means full agreement once again. For the upcoming results or examples, we used for the images an ensemble of 5 convolutional neural networks with resonant architecture. And for the text example, an ensemble of 5 fully connected neural networks. The examples were taken from the CIFAR10 image dataset and the large movie review dataset. For each experiment, we derived in total 100 linear regression models as surrogates using the standard Lime parameter setup. Now, on top is depicted the standard Lime surrogate explanation that we would obtain if we were to use simply Lime. And in the bottom row, you can see the aggregation of the diverse surrogates by running Lyman multiple times and aggregated through this rating scheme. And we can see that by aggregating the surrogate explanation and then also reporting the consensus among these surrogates, the user is provided with more information to reason about this explanation. So for instance, we could inspect the mean rank that has been assigned to the superpixels here, given in the bottom row second image. And then based on this mean rank, we could infer about the order of importance. So again, here we would see that, okay, the bottom left superpixel has been on average given the highest rank to, so this would be of highest importance. And the top right one would be given the lowest rank to, so of least importance. Now by reporting the ordinal consensus or the level of agreement, we can then also see how certain we can be about reasoning about the importance of the superpixel. So here we can see the ordinal consensus being rather high for the bottom left superpixel. We can be certain about the importance assigned to this one. The order of importance for the superpixels here shown in this lighter orange region is not that clear, because there seems to be a rather high disagreement among the surrogate explainers with regards to the ranking of these superpixels. By inspecting the overall consensus with regards to all superpixels through Clarence coefficient of concordance, short W, and Fleiss kappa, short kappa, we could also compare different image segmentations or segmentations which perhaps lead to a more trustworthy explanation. For instance, the top row would again show the explanation which you have seen in the previous slide. The second row shows an explanation derived on the image being segmented into 8 different superpixels. And now by inspecting the values W and kappa, we can see that there's an overall more agreement among the surrogates derived using this segmentation. So this segmentation is perhaps more trustworthy as compared to the one depicted on the top. In the bottom row, you see the image segmented into fewer superpixels, for instance, 3. And by inspecting W and kappa, we could then also see that by segmenting the image into fewer pixels, we would also obtain more trustworthy explanation. Stepping away from images and coming to line on text, for a text example, the explanation would be given in the form of words. So in a text, the feature importances would be given to individual words. And again, by running TextLime multiple times, we would end up with this distribution of surrogate coefficients, which is here depicted on the left. And by aggregating the surrogate coefficients through this rating scheme, we could then see the mean ranks that have been assigned to these words. And on top of that, by reporting the ordinal consensus, we can see that this can serve as a proxy measure of words having been assigned very different surrogate coefficient values to. For instance, if we looked at the words tight and attempts, the distributions of these surrogate coefficient values is rather large or has a high variance, and also the distributions overlap, which is then also reported by the ordinal consensus as the amount of trust or the amount of consensus among the surrogates with regards to these words is rather low, as the consensus has values at about 0.5, 0.6. So concluding from this, can say that by reporting the consensus, additionally to the explanation, the explanation is overall enriched, and the user is provided with more measures or more tools to reason about the explanation. For instance, in the case of images, these consensus estimates can help in order to give the user feedback on which segmentation of the input into interpretable components might lead to a more trustworthy explanation. These are the references. Thank you very much.